section 5.2 is titled Logarithm Functions. And yesterday we graphed the exponential function. F of x equals 2 to the x. So let's just put that back up on the board here. And so remember, it crosses the y-axis at y equals 1. So here's x equals 1, x equals 2, x equals 3, x equals minus 1, x equals minus 2, and x equals minus 3. And then we have 1, 2, 3, 4, 5, 6, 7, 8. And so the 0.38 is on the graph. Crosses the y-axis, right, at y equals 1. And then the point minus 318 is on the graph. And so remember, the graph looks something like this. Okay? This is the point minus 318. This is the point 0, 1. And this is the point 38. And you can see from the graph of that exponential function, it passes the horizontal line test. And so it has an inverse function. Well, given the graph of a one-to-one function, how do we get the graph of its inverse from the graph of the one-to-one function? You remember? You switch the x and y coordinates, right? So the 0.38 is on the exponential function, and so the 0.83 is going to be on its inverse. Okay, so we got to go out here. 3, 4, 5, 6, 7, 8. X equals 8. Okay, and then up 3 units to y equals 3. And there's the 0.83. Okay. Switch, right? And then for the y-intercept, right, we switch the x and y coordinates and we get to 0.10, which is right here. And then for the point minus 318, when we switch the x and y coordinates, we get to 0.18 minus 3. Well, 18, x equals 18 is just to the right of the origin. Okay. And then we gotta go down 3 units to minus 3. And now we draw a smooth curve through that. Okay. So this is the point 83. This is the point 10. And this is the point 18 minus 3. Okay. And remember, the inverse function is a reflection of the one-to-one function across the diagonal line y equals x. So here's the diagonal line y equals x. Okay. It's hard for me to see how I did, standing right next to the board, but I guess that's not too bad. Okay. So this is the graph of f of x equals 2 to the x. Okay. And this is the graph of its inverse, f inverse of x. Okay. So given the graph of an exponential function, right, all you gotta, to find the graph of the inverse, all you gotta do is switch the x and y coordinates and plot those points and like connect the dots. Okay. So now we know what the inverse function of this exponential function looks like. Okay. You know what its graph looks like. Let's find the algebraic expression for that inverse function. Okay. So you know how to find an inverse function. That was on exam 2, or was it exam 3? It was an exam we just took, right? Exam 3. First question, I think, right, on the exam. Right? Had to find an inverse for a rational function. So you know the steps. Replace f of x with y. And then you switch x and y. So x is equal to 2 to the y. And then third step, solve for y. There's a problem. At this stage, at this point, there's no algebra to solve for y. Okay? So what do? So mathematicians way back when created a function that is the solution to this equation. Okay? And that solution, that function they created, is a logarithm. It's the logarithmic function. The logarithmic function is the solution to this equation. Okay? So this equation can be read y is the exponent of the base 2 that produces x, right? Y is the exponent of the base 2. Remember, this is an exponential. 2 is the base. So y is the exponent of the base 2 that produces the value x. Okay, that's how you can read that. Well, we're going to swap out the word exponent here for the word logarithm. Okay. And so now we can write y is the logarithm of the base 2 that produces x. So we just swapped out logarithm for the word exponent. Henry, how much of that can you see?
I can see it all.
You can see the whole thing?
Yeah.
Just don't go any lower?
Yeah, that's good.
Okay, don't go any lower. Okay. So the notation for this function, right, that equates x to 2 to the y power is y equals log base 2 of x. So we're using the three same numbers, x, 2, and y, and we're expressing the solution, y, with this fancy notation, log base 2 of x. Okay? So this is read y equals log base 2 of x. And that's our fancy function, our fancy notation for the solution to this equation. Yes, ma'am.
Is x raised or is it times the log?
Say that again.
For the x,
No, x is the input.
it's regular, okay.
Yeah. So you know how x is the input to the function f? X is the input to the log function.
So it's like same size.
Yes.
Okay,
But 2 is a subscript.
okay, gotcha.
Okay, you guys get that? That's important because people miswrite this stuff on exams and stuff. 2 is a subscript on the word log. Okay. So it's log base 2 of x. Okay. All right, so that logarithmic equation, log base 2 of x, and x equals, right, to the y. So this is a logarithmic equation. This is an exponential equation. Okay. These two equations are equivalent. What does that mean? That means if this equation is true, then this equation is true. If this equation is true, then this equation is true. Okay. So we can write if y equals log base 2 of x is true, right? Then x equals 2 to the y is true, okay? And vice versa. Goes the other way too, right? If x equals 2 to the y is true, then y equals log base 2 of x is true. Okay? Because to get this equation, all we're doing is rearranging the numbers in this fancy notation. And to get this equation, all we're going to do is rearrange these numbers. Okay? All right. So the logarithmic function, so in general, okay, the logarithmic function with base a greater than 0 and not equal to 1, okay, is defined by y is equal to log base a of x if and only if x is equal to a to the y. Okay. Now, what does if and only if means? What I wrote over here. If y equals log base a of x is true, then x equals a to the y is true. And then it means it's true the other way. If x equals a to the y is true, then y equals log base a of x is true. Okay. So let's look at these two equations, how they're set up. Okay. So we have the exponential equation. Okay. X is equal to a to the y power. Okay. So in this exponential equation, right, a is the base, right? We're talking generalities now, right? We're not plugging any numbers in. A is the base of the exponential. Y is the exponent in the exponential. And x is the value of the exponential. Okay. With a logarithmic function, right? The corresponding logarithmic function. Oh, so let me right? So in words, right, what we have is value of the exponential function is equal to the base raised to the exponent, right? That's what we got in words, okay? Base raised to an exponent equals the value of the exponential. Okay. Now with a logarithmic function, we have y is equal to log base a of x, right? So the y here on the left is the exponent, right, from the exponential. Are you raising your hand?
Yeah.
Okay. And a is the base from the exponential, okay? And x, that's the input to the log function, okay? Just like, I gotta remind you, right? X is the input to the function f, right? So x is the input to the logarithmic function, okay? It plays the same role as x here, okay? And x that goes into the logarithmic function is the value of the exponential. So in words, with the logarithmic function, we can write exponent is equal to log base of the value of the exponential. Okay. And sometimes we put the input to the log function in parentheses, right? We can do that. So, right, so here's the exponential equation. I said logarithmic function. I think I'd rather say logarithmic. It doesn't matter. But just so I'm using equation in both those guys. So over here, right, we're expressing the relationship between the exponential equation and logarithmic equation in words. And here we're showing it with variables, okay? With numbers. Okay. Any questions on that, ladies and gentlemen? Okay. All right, so let's take a look. Let's do some exercises with real numbers. So this first exercise, we're going to write each logarithmic statement as an equivalent exponential statement. Okay. And so remember, x equals a to the y, and y equals log base a of x, okay, are equivalent equations. So the first one is log base 3 of 9 is equal to 2. Now, how would I determine whether that's a true statement or not? I would convert it to the exponential statement, because I know how to work with exponentials. And if the exponential is true, then I know the logarithmic statement is true. Okay. So in this logarithmic statement, the base a is equal to 3. The value of the exponential x is 9. And the value of the exponent y is 2. Right? Just matching this up with this. Okay. Now the The difference, I guess, between this one and this one is I've switched the left and the right hand side, right? You know, we can do that. So a is equal to 3, x is equal to 9, and y is equal to 2. So now I plug in for x, a, and y in the exponential statement, the equivalent exponential statement. And I get 9, right? X is equal to 9, and a is equal to 3, and y is equal to 2. Does 9 equal 3 squared? Yeah. So if this is true, then this has to be true, okay? They're either both true or both false, right? So to determine whether a logarithmic statement is true, I convert it to an exponential statement and see if it's true there, okay? And so you can write 9 is equal to 3 squared, or 3 squared is equal to 9. Okay. Next we have log base 8 of 2 is equal to 1/3. So in this logarithmic statement, you can see a is equal to 8, x is equal to 2, and y is equal to 1/3. And so again, see whether this is a true statement. We plug in for x, a, and y up here and see if we get a true exponential statement. And so x in this case is 2, a is equal to 8, and y is equal to 1/3. True or false? What does 1/3 power mean?
Cube root.
Cube root, right? So 8 to the 1/3 is the same as cube root of 8. Is the cube root of 8 equal to 2? Yeah. Okay. So the equivalent exponential statement is 2 is equal to 8 to the 1/3, or if we switch the two sides, 8 to the 1/3 is equal to 2. Yeah. So when I'm solving problems with logarithms, I often go write the equivalent exponential statement because I know how to work with exponentials. Okay. We're not really taught to think in terms of logarithms. All right. In the next exercise, we're going to do the opposite. We're going to write each exponential statement as an equivalent logarithmic statement. And so we have 0.001 is equal to 10 to the minus third power. Is that a true statement? So x in this case is 0.001. A, the base, is 10, and y is equal to minus 3. So to see whether that's a true statement, true exponential statement, right, you might have to do some work on the side, right? 10 to the minus third power is 1 over 10 cubed, okay? The rules of exponents. 10 cubed is equal to 1,000, okay? 10 times 10 is 100, times 10 is 1,000. And then, how many decimal places to the right of the decimal goes to 1? Well, 1/10 would be 0.1. So 1/100 would be 0.01. And so 1/1000 would be 0.001. Right? 10, 100, thousands. Right? So 1/1000 is 0.001. And so this is a true statement. Okay? So the corresponding logarithmic statement, y is equal to -3. The base is 10, and the value of the exponential is 0.001. Okay. So log base 10 of 0.001 is equal to -3. And you can write it, you can switch the two sides, right? Log base 10 of 0.001 is equal to -3. Okay. You switch. We often do that. Next we have 5 is equal to a raised to the -1 power. So the base a, right, is not specifically given. X is equal to 5. Y is equal to -1. Okay. So substituting in for y and x, we have -1 is equal to log base a of 5. Now, if you were given this logarithmic statement and asked solve for a, what you would do is write the equivalent exponential statement. And we know how to solve for a in this equation, right? That's just basic algebra. Okay. So once you solve the exponential equation for a, you now have the solution for a in the logarithmic equation. Okay. And often that's how we solve problems with logarithms. All right. Any questions on that, ladies and gentlemen? Okay. All right, you don't have to redraw the graph. Unless you want to. But we drew the graph of log base 2 of x, right? And from that graph, okay, we can get the properties of the logarithmic function. F of x equals log base a of x, okay? So this was, we graphed log base 2 of x, but what we're gonna write applies to all the bases for the logarithmic function, okay? And the first one is the domain of the function is x, right? Remember, x is the input to the function, right? Just like x is the input to f of x. Okay. The domain, what numbers can you put in for x in that logarithmic function? Any real number greater than 0. Okay. So the domain is all real numbers greater than 0. Okay. So what does that tell you right away? You can't take the log of 0, and you can't take the log of a negative number. Right? What goes into the log function here, right, for x has to be a positive number. Okay. The range, well, look at the graph, right? We know how to find the range from a graph. It goes down forever on the left, right? So there's no minimum y coordinate. And it actually goes up and to the right forever. But it goes up really slowly. But there's no maximum y coordinate. Okay, it never maxes out. And so the range is all real numbers. Over here on the domain, as the graph goes down, it gets closer and closer to the y-axis, but it never touches it. Okay. As the graph goes down, it gets closer and closer to the y-axis, but it never touches it. Okay. So the x-intercept right? It crosses the x-axis at the point x equals 1, or the ordered pair 1, 0. And then as I just noted, right, as the graph goes down, it gets closer and closer to the y-axis, and the y-axis and the vertical line, x equals 0, right, coincide. And so the vertical asymptote is the vertical line, x equals 0. Which coincides with the y-axis. And remember, vertical asymptotes are vertical lines. Okay. All right. And you can see that the function is continuous. You can trace it out without lifting your pencil off the paper. And it also passes the horizontal line test. So it has an inverse, and its inverse is the exponential function. Okay. So we had them both up on the board, right? So this is the inverse function for the exponential function, and the exponential function is the inverse function for the logarithmic function, right? They're inverse functions of each other. Okay. All right, let's look at some other properties of logarithms. So those are the properties of the graph of the basic logarithmic function. Let's look at properties, other properties. Involving numbers, okay? One is, so the first property, the log of 1 in any base, right? So log base A of 1, remember A is greater than 0, not equal to 1, okay? Is always equal to 0, okay? So remember, the base A in our equation is always greater than 0 and not equal to 1. Okay? So it's a positive real number not equal to 1. Okay? And the log base A of 1, regardless of the base, is always equal to 0. Because if you write this in exponential form, right, you get the base A raised to the exponent 0 is equal to 1. And you know, any non-zero number raised to the 0 power is always equal to 1. Okay. The second property is that log base A of A is always equal to 1. Because when you write this as an exponential, you get A raised to the first power is equal to A. Right? So any number raised to the first power is just equal to itself. We know that to be true. Okay? So it's very important that you understand the connection between the exponential statement and the logarithmic statement. Because that's how I verified that logarithmic statements are true, right, the exponential statement. Okay. The third property, we have x is equal to a raised to log base a of x. Now, how did I get that? Okay. Well, let's put our equivalent equations up on the board. Okay. X is equal to a to the y. Okay. And y is equal to log base a of x, right? So if I replace y is equal to log base a of x, so if I replace y here with log base a of x, I get x is equal to a raised to the log base a of x. Okay. So got this by substituting log base a of x, okay, for y in x equals a to the y power. Okay. And that's true for any base a. Okay. So a raised to log base a of the input is just equal to the input. Okay. Remember, x is the input to the log function. And then the fourth property is y, the exponent y is equal to log base a of a to the y power. Okay. So log base a of a to the y power, so the input is a to the y power now. Okay. And log base a of a to the y power is just equal to y. And how did I get that? In y equals log base a of x, I just replace x with a to the y, because that's what it's equal to. So I put a to the y in for x over here. We get log base a of a to the y is equal to y. Okay? And so those are four important properties. Okay? So let's use those in a couple of examples. I don't want to erase anything, but I have to. I want to leave the properties up. Okay. So in this exercise, we're going to simplify each expression. So we have log base 2 of 16. Now there are a couple different ways of solving this, right? Log base 2 of 16 is equal to what? Okay. Yeah, it looks a lot like property 4, doesn't it? Log base 2 of 16. Over here we got log base 2 of, right, log base of a to the y. Right? So it looks like property 4 with a equal to 2. Well, you might note that log 16 is equal to 2 to the 4th power, right? 2 to the 4th power is equal to 16. And so a is equal to 2, y is equal to 4 in property 4. So this is just equal to 4. next we have, 3 raised to log base 3 of 7 is equal to 1, right? So the exponent is log base 3 of 7. Okay. So we have 3 raised to log base 3 of 7. What does that look a lot like? Property 3, right? Where a is equal to 3 and x is equal to 7. And so 3 raised to log base 3 of 7 is just equal to the input 7. So this is just equal to log base 3 of 7 is just equal to 7 by property 3. And then we have log base square root of 3 is square root of 3. So log base square root of 3 is square root of 3. What's that equal to? Well, that looks a lot like property 2, doesn't it? With a replaced with square root of 3. So log square root of 3 of square root of 3 is just equal to 1. And last but not least, we have the log base 6 of 1 is equal to what? The log of 1 in any base is equal to what?
0.
0, right? Property 1. So that's the application, right, of those four properties, okay? All right, so let me get attendance real quick, like, and we'll get jump on the weekend.